And for the next presentation, I think that we have to invite Dr. Shadafar, Mehdi Shadafar, to give his lecture for the audience.
Yeah, thank you so much. Do you have my voice here right now?
Yes, yes, that's nice. We have that.
Sure. So I try to share my screen. If you give me a minute, you may have my screen right now, right? Do you have my screen? Excellent. Okay, I'll start my presentation. I would like to appreciate the opportunity given for attending this conference. Here I would like to start my lecture on the probabilistic assessment of the ground vibration induced by a rock explosion. This job is done together with my colleague Dr. Hassani and Dr. Kurdistani from Iran and China. As you can see with the title here, we are going to talk about the ground vibration, which is caused by the rock explosion, but at the same time we are going to do it in a probabilistic way. That means we are facing some sort of probability analysis. Okay, I go through the first slide. First, I'm going to show you how this explosion will happen and how the vibration may propagate into the surrounding media. Just imagine that this point I'm showing here is the explosion point. It's like the explosive charge is just placed right at this point. And around it, we do have the blast hole. So as you can see, the blast hole is slightly larger than the explosive charge in order to make it easier to just put and place the explosive charge into the blast hole. Once the explosive charge goes off, there would be a part of cracks propagating into the rock that we call it crash zone. I just named it crash zone because it is not a single or like a few number of cracks. It's just a zone full of cracks and interconnected, which make this zone totally unstable. So we call it crash zone. But there are a few number of cracks going beyond the crash zone that are just shown here by these few lines here, and we call them radial cracks. So radial cracks are those that propagate further into the rock media and make a zone called the crack zone. So until now we are facing two zones. One is the crash zone, which is full of interconnected small little cracks, and then beyond that we have the crack zone, which contains some sort of radial cracks. But when we go beyond these two zones, then we don't have such a cracking problem and issues, and we only have the ground vibration. So currently we are not going to focus on these two zones. Those are also of importance, but we are not going to focus on them here. We are just want to talk more about the ground vibration and try to understand what would be the ground vibration. And we are, as I told you, we are going to work on it in a probabilistic way. Okay, these are just a few of models developed in the literature by different researchers, showing us the relationship between some sort of variables and something that I just termed it here as V. V is actually the velocity, or more specifically, it is the peak ground velocity that we usually call it PGV in earthquake engineering when we face the earthquake. But here we are facing the explosion, but it is again the PGV. So PGV is a better representative of the explosion because the explosion load, although it is a dynamic load, but it happens in a fraction of a second. So the acceleration would not going to be a good variable to represent the explosion, but we prefer the PGV or sometimes TGD, but mostly PGV in the literature. So this is just the equations in the literature. But what we are going to do is just summarized here. We are going to select a primary model as deterministic, and then we further go through defining something called limit state function, which is the border of failure and safety zone. And then we further go through the Monte Carlo simulation in order to transfer the deterministic to probabilistic model. And then we further create a large data set of model response that we usually call it random realizations. We further try to approximate the exceedance probability, and we finally develop something called exceedance probability curve, which is a really complete definition of probabilistic assessment of current vibration. Okay, let's dive into it. Here is the relationship that I chose from the literature in order to represent the deterministic model. I chose this one because this is a more complete model and it contains many variables, including the R, which is the monitoring distance. It's like the distance from the explosion point that we are going to assess the vibration intensity. And then we further have the W, which is the maximum charge per delay, which means how much explosive charge we are going to use is something like that. And B is the burden, which is the burden above the explosion point. And we additionally have a few number of parameters like K, B, and gamma, which needs to be calibrated based on a specific site. So for that, I just chose a mining site in India, and I got the value of KB and gamma as this value shown here. So having this deterministic relation in hand, I further go through the reliability model. So as I told you, for the reliability model, we need a limit state function. As a simple way, I just define the LSF as R minus Q. That R is a threshold, it's a certain threshold. For instance, I could say 10 meters per second is a certain threshold of the PGV. And Q is exactly that relation, is the deterministic model that I just showed you in the previous slide. So if I introduce these two into the LSF model, we're gonna get the LSF as this one. So I'll put R as 10, it's like I chose a certain threshold, like 10 meters per second, and I just use the deterministic model to replace the Q. And currently we have the LSF defined as you can see here. And for the next, I can calculate the failure probability. That sometimes we call it exceedance probability. I will tell you why. When the LSF is less than 0, it's like when the LSF is a negative value, means Q is greater than R, means the vibration in the medium is greater than the threshold we think. So in other words, the vibration exceeded the threshold, and that's why we call it exceedance probability. So let's go through the Monte Carlo simulation, how we're gonna calculate this probability. Actually, there are plenty of methodologies available in the literature to calculate exceedance probability, including the first and second order reliability approach. However, we're gonna use the Monte Carlo simulation in this formulation that I'm just showing to you concisely here. The F is the probability distribution function, the joint probability distribution function over the whole variables, and psi is what we call it the step function, which can be 1 when LSF is positive and 0 otherwise. And yeah, this F is the distribution function. And upon utilizing the Monte Carlo simulation, the PF can be calculated as the amount of cases, the count of cases that psi is positive over n, and if we calculate this one, we can get the failure probability. So here are the variables involved in the problem. I just define them as random variables. So for R, I use the log normal, for W, log normal, and for B, I use a discrete variable. And the mean and the standard deviation are all defined here. So let's proceed to the Monte Carlo simulation. I'm going to use 20,000 random samples, and I just set the R as 10. Considering these two assumptions, then as you see the blue bar chart here, or the histograms here, are showing me the realizations of the Monte Carlo simulation. But there are a little portion of red bars here. Also, you can see it here. Those are exactly the cases that LSF is less than 0. And this is the histogram of the PGV peak particle velocity (ppv), and you can see the red parts here. If I count the number of the red parts and divide it by the total number of cases, I can get the failure probability. I just did it here. You can see the failure probability is almost 3.4%. So the definition of this probability is the exceedance probability corresponding to the threshold 10 meters per second. That means the probability of getting the vibration equal or greater than 10 meters per second is going to be only 3%. But we just solved the problem, right? But the point is, we just get the probability for a fixed threshold. But what about the other threshold? I will tell you later. And this graph is showing us the convergence of the Monte Carlo simulation. We just used 20,000, but in fact, maybe 8,000 is almost enough, because after 8,000, we have a negligible variation in the exceedance probability. So it just ensures that the failure probability we calculated is accurate. So, but the next step is to go beyond the calculation for one threshold, and we calculate it for different thresholds. This is just the other stuff I showed you. What we are going to do is to make the R as a decision variable. We are going to change this one and then repeat the Monte Carlo simulation. So here is the different value of D, and then we calculated the exceedance probability corresponding to each value of VD. Considering a step slightly smaller than what I just showed you in this table, we can put them in a graph. So here is the PPV, and here is the exceedance probability. So I just draw PPV versus exceedance probability, and this is what we call it exceedance probability curve. As you can see here, for instance, for the PPV5, we have this amount of exceedance probability, and once the PPV get larger, the exceedance probability drops sharply. And in order to show you exactly what this graph is, each point on this graph corresponds to a complete Monte Carlo analysis. For instance, you can see the graphs I showed here, and I'm showing you the convergence of this graph at each point. So at each point, we are generating over 20,000 random samples for each point. So this graph is going to be a time-taking process, but it gives us a really excellent information. So for the next, this graph that I just showed you here correspond to certain like probabilistic characteristics of random variables. For instance, certain mean, certain standard deviation. What I'm going to do is to change the mean of variables and again repeat the whole analysis and develop the whole exceedance probability in the whole PPV region in order to do something called reliability sensitivity. So you can see the results here. For instance, by changing the mean of R, I got different exceedance probability curves showing me the PPV versus the exceedance probability for different value of the mean of R. And similarly, I did it for different value of W, and then again I calculated the PPV. Right now, if I calculate the difference between these curves, I'll come up with a new graphs showing me the maximum effect of each parameter. For instance, the maximum effect of R on the exceedance probability can be shown here. The maximum effect happening between something like maybe 5 millimeter per second, or here is like more or less the same for the W. So we can understand that the R and W are type of important parameters, but their most important, their highest influence happen in the range like between 0 to 10 millimeter per second. But when we go through the B, which is the burden, and I conduct the reliability sensitivity and calculate the difference, I can see that there is not much effect of the B on the failure probability, maximum 2% maybe. And so I can actually understand that currently the peak particle velocity may not be that important parameter. See, what I'm trying to insist here is that such a conclusion may not be easily reached by the deterministic approach, because different parameters are in different scales, in different units. But when we come into the probabilistic things, we can get the effect of each variable on the failure probability, and thus we can compare variables to one another. So here is the conclusion and summary. What we did was defining the peak ground velocity as the peak particle velocity as a reliability model. Then we established the reliability and solved it by the Monte Carlo, and further we developed the exceedance probability curve, and finally we conducted a sensitivity analysis to understand what would be the effect of each parameter on the exceedance probability of the PPV. My last word is the future research line. Just imagine that we currently have the exceedance probability, right? So if we have the cost function, what means by cost function is like what would be the cost if we get to a certain amount of vibration. If we can have this cost function, then we can put them together with exceedance probability in order to get the probabilistic risk assessment. That means what would be the probability of getting a certain risk when we have a certain amount of PPV. And this is the conclusion of our research that we are currently working on. Thank you so much for your attention. I just tried to be fast and be concise in order to save the time. If there's any question, I would be available to answer. Many thanks.